Good evening, friends. Today we are going to discuss here the unit number 2, which is set theory. So basically, what is meant by set? So set is collection of object of any sort. Means, for example, maybe the collection of natural numbers, maybe the pair of shoes. And talking about collection of object of any sort, it may be of similar type of object or different types of object. Some examples of the sets are set of lines, set of triangles. You can see a set of line, set of triangle. These are the examples of set. Then any object belonging to the set is called as a member or element of that set. Means, for example, let us consider we have taken capital N is equals to 1, 2, 3, 4 up to infinity. Actually, it is an infinite set which containing the natural numbers. So that one is belongs to capital N, 2 is belongs to capital N. So that 1, 2, 3 and so on are nothing but members or elements of that set. Generally, the set is represented by uppercase alphabet from A to Z. So uppercase alphabet or capital letter, which is notation for set, and lowercase letters A to Z, these are nothing but the members or elements of the set. And let us assume two elements P and Q we are talking about. So if P is the element belongs to A or P is the element present in the set A, then it is written as P is belongs to A. This is the symbol for belongs to. This is the symbol for belongs to, and which is read as P belongs to A or P is in A or P is an element of A. So that is P belongs to A. Then again consider if Q is the element which is not present in the given set A, then it is written as Q is not belongs to A. So that is the symbol for not belongs to A. So these are nothing but the belongs to and not belongs to the set. So the negation of the statement, let us consider Q is in A. For example, Q is in A is negation of Q belongs to A, because negation of the statement Q is in A, that is negation of Q belongs to A, which is same as Q is not belongs to A. You can see here Q is not belongs to A. We have to mention the set S is equals to 1 to A. So if I take here one set that S is equals to 1 to A, means 1 to A, these are the members of S, then you can mention here 1 is belongs to S, 2 is belongs to S, and A is belongs to S. Means 1, 2 and A are the elements present in the set S. And this is the method which is used for finite set, because it containing finite number of elements. That's why it is the method used for finite set. Whenever there are infinite number of elements, for example, as I mentioned earlier, natural numbers, in that case we are using predicate method. And the predicate method is, you can see one set S which gives you X such a way that X is a odd number. So there is no restriction or there is no limitation for odd numbers. Generally odd numbers you can mention here 1, 3, 5, 7 in the positive numbers, and negative -1, -3 and so on. So predicate method is generally used for infinite set. So that is the predicate method, and this was the regular method which is used for finite set. Again, this second example, S1, which is again X such a way that X is a odd number, and so on. You can see here predicate method. Then some example or some types of set. The first one is this finite set. The set which containing finite number of elements or finite number of object is called as a finite set. The set which containing finite number of elements or finite number of objects is called as a finite set. So earlier whatever the examples we have taken, that is the example of finite, that is A is equals to 1, 3A. A is equals to 1, 3A is the example of finite set. Then infinite set, collection of natural numbers, means whenever number of elements or number of objects in the given set is infinite, then it is called as a infinite set. Fine. Then inclusion and equality of set. So what is meant by inclusion and what is meant by equality? So let us see here one by one definition of the inclusion. So see here definition of the inclusion. Let us A and B any two sets. If every element of A is an element of B, then A is called as a subset of B, or A is said to be included in B, or B includes A. Fine. So that is the definition of inclusion. That is the definition of inclusion. Means what they have given. Consider A and B, these are the two sets, and all the elements of A are present in set B, then A is said to be subset of B, or A is said to be included in B, or simply you can say B includes A. So that is nothing but the inclusion, or you can say here subset. You can say here A is a subset of B. Fine. Then equality of set. So what is meant by equality of set? When the given two sets are said to be equal. For example, A and B, you can see here, you can see some examples are given to you. A is equals to 1, 2, 3, that is the first set. B is equals to 1, 2, C is equals to 1, 3, D is equals to 3. Then what you have to find out? Equality. So keep in mind that set itself is equal to that particular set. Means A is equals to A, B is equals to B, C is equals to C, and D is equals to D. Fine. Now talking about inclusion, so you can mention here, or you can see here, B is included in A, because all the elements of B are present here A. You can see here B is included in A. Likewise, C is included in again A. D is included in A. Fine. Because A is a superset as compared to B, C and D. That is nothing but the inclusion. What is meant by equality? Simply, all the elements, consider two sets are given to you, A and B, these are the two sets given to you. And if equal number of member functions or if equal number of elements are present in both A and B, then A and B are called as a equal set, or they are called as a equality of set. Fine. So you can see here equal set. What they have given? Two sets A and B are said to be equal if and only if A is a subset of B and B is a subset of A, or symbolically A is equals to B, which is equivalent to A is subset of B and B is a subset of A. Then A and B are called as equivalent to each other. What I mentioned here, A should be subset of B, B should be subset of A. If both the conditions are satisfied, then symbolically it is represented as A is equals to B, and then it is called as a equal sets. Fine. So that is the equality of the two sets. Then what is meant by proper subset? So basically, what is the difference between subset and proper subset? In the case of subset, there was no restriction with respect to number of elements in the superset and number of elements in the subset. There was no restriction. But in the case of proper subset, what is the terminology? For example, if A is the set, see, A is the set, A is called as a proper subset of B. A is called as a proper subset of B if A is a subset of B and A is not equals to B. Then it is written as A properly included in B, so that A properly included B, which is equals to A subset of B, and A should not be equals to B. So that is the thing with respect to the proper subset. For example, if A containing two elements 1, 2 and B containing three elements 1, 2, 3, then A is said to be proper subset of B, because all the elements of A are present in B and B having one more element as a 3. That's why B is called as a superset, A is called as a subset, and the relationship between A and B is called as A is a proper subset of B. Keep in mind this. There is a difference between proper subset and subset, and this is the notation for proper subset. You can see here A proper subset of B, and also called as a proper inclusion. Proper subset is also called as a proper inclusion. Now universal set. So what is meant by universal set? Just wait. Universal set. A set is said to be universal set if it includes every set under the discussion and it is denoted by E. For example, let us consider capital E is the universal set. When it is said to be universal set, for example, A, B, C, D, these are the four sets which are under the discussion of E, such a way that A is equals to 1, 2, 3, B is equals to 1, 2, C is equals to 1, 3, and D is equals to 4. Then E should be 1, 2, 3, 4, because if I take E as a 1, 2, 3, 4, then it will be include all the sets A, B, C, D. So that's why that E is called as a universal set. Generally, E is the notation for universal set, as well as capital U is also used for universal set. Keep in mind. So you can see here, if A is the set, then A is a subset of E. Absolutely. If A is a set, then A is a subset of E, where A is the regular set and E is the universal set. So X belongs to E, where E is equals to X, such a way that P of X or negation P of X. So that is the representation for universal set. Then next one, null set. What is meant by null set? For example, if one set given to you and it does not containing any element, then it is called as a null set. Or you can say, if the set having the cardinality equals to 0, then that set is called as a null set. Generally, it does not containing any element or it does not containing any object. It is represented by phi. It is represented by phi. And phi is equals to, how to represent phi? Phi is equals to, or simply it is also represented as opening and closing curly. Fine. So phi is equals to X, where P of X and negation P of X. So that is the notation, P of X and negation P of X. So that is the notation to represent the null set. Then what is meant by power set? For example, let us consider one set is given to you. One set is given to, let us say, A is the set given to you, and which containing two elements. For example, 1 and 2, these are the two elements belongs to the A. Then what will be the power set of that particular A? So power set is nothing but all the possible subsets which is made up of the given element in the existing set. For example, you can see here, if given set is A, then the null set phi and set A are subset of A are also any element of A is belongs to A. So rather than this, you can see here one definition. For a set A, collection or a family of all the subset of A is called as a proper subset of A, and it is denoted by P of A or 2 raised to A. It is denoted by P of A or 2 raised to A. So P of A is equals to P of A is equals to 2 raised to A. So here A is nothing but number of elements or number of members present in the set, which is nothing but X, where X is belongs to A. Okay, fine. Power set of null set phi having only element phi. So power set of phi is equals to only a phi. Yes. So that is the terminology which is related to the power set. Fine. Now, one more example I would like to mention here. For example, see, S2 is the given set. S2 is the given set which containing two elements A and B. Then what will be the power set? So definitely it containing two elements A and B. So cardinality of that set will be equals to 2. And what will be the cardinality of the power set? 2 raised to 2. 2 raised to number of elements present in the given set. So 2 raised to 2, which is equals to 4. So 4 possible subsets will be there. And that subsets are phi, opening and closing curly A, opening and closing curly B, opening and closing curly AB. Fine. So these are the 4 elements are nothing but subset which with respect to the original set S2, and P of S2, which is nothing but power set which is denoted as like this. So keep in mind this one. Whenever the question will be asked with respect to the power set, you have to mention this one. Fine. Power set is nothing but collection of all the possible subsets from the element of the given set, which is nothing but P of A or P of set, which is equals to 2 raised to number of elements. Fine. Now, so talking about, so these are the some basic terminologies which is related to the set. Now we are going to discuss here one by one types of operations which is performed on the set. So basically there are 7 operations: union, intersection, then complement, absolute complement, relative complement, symmetric difference, Boolean sum. Okay, so these are the some operations. So let us see here what is meant by intersection. Very first operation. For example, if A and B are the two sets, then intersection could be written as A intersection B, that is elements belongs to both the sets. In the intersection we are taking common elements only. Fine. So A intersection B, that is elements belongs to the both the sets, and which is denoted as A intersection B, which is equals to opening curly X such a way that X is belongs to A and X is belongs to B. So that is nothing but intersection. Fine. Intersection follows commutative law as well as associative law. It follows commutative law as well as associative law. So you have to show here it follows commutative law means what? You have to show that A intersection B is equals to B intersection A. So that is our motto of commutative law. So as we know that X is belongs to A intersection B, so you can write here which is equivalent to X belongs to X such a way that X is belongs to A and X is belongs to B. Fine. So it is simply written as X is belongs to A and X is belongs to X is belongs to A and X is belongs to B. You have to correct over here. X is belongs to A and X is belongs to B. So as we know that this is nothing but we are going to take here one connective, that is ANDing, and it ANDing follows commutative law. So we are interchanging likewise. We have taken this X belongs to B over here and X belongs to A over here. And finally, by substituting the values, you can mention here this X belongs to, in curly bracket, X such a way that, or X where X is belongs to B and X is belongs to A. So simply you can write this as a intersection. It is also follows the associative law. You can check for this one also. That is the intersection. Now talking about disjoint. So what is meant by disjoint? When the given two sets are said to be disjoint. For example, if A and B, these are the two sets, A and B are said to be disjoint to each other if A intersection B is equals to 5. Means if there is a no common element between A and B, then A and B are called as a disjoints of each other. You can see here A intersection B is equals to 5, or you can see here A and B have no elements in common. That is called as a disjoint. Fine. Then what is meant by mutually disjoint? So in the previous point we have seen what is meant by disjoint. In the case of mutually disjoint, we are talking about more than two sets. For example, A, B, C, you can see here, if A, B, C, these are the three sets, such a way that A intersection B is equals to 5, B intersection C is equals to 5, and C intersection A is equals to 5, then ABC are called as mutually disjoint of each other. So that is the concept with respect to the mutually disjoint. You can see here, a collection of set is called as a disjoint collection if for every pair of set in the collection, two sets are disjoint. So that is the formal definition. What you have to keep in mind, whenever there are more than two sets are given to you, if you take the alternative two sets with each other and if you perform the disjoint, it gives you 5, then all these set together is called as a mutually disjoint to each other. Fine. Now take the fourth operation, that is a union. So what actually we are going to perform in union? Consider A and B, these are the two sets, and you have to perform union operation. Then it is represented as A union B. And what is meant by A union B? A union B, which is equals to x such a way that x belongs to A or x belongs to B. Here is the or in condition. Either x should be present in A or x should be present in B. If it is present in both the set, you have to take it for once. Okay, you should not be repeat element while taking the union. You have to take for once. So what is A union B? A union B is equals to x, where x is belongs to A or x is belongs to B. It is also follows commutative law and associative law. You have to prove this. It follows associative law and commutative law. Fine. So what is the commutative law? You can see here. This is the commutative law. A union B is equals to B union A. And what is associative law? A union in bracket B union C, which is equals to in bracket A union B union C. That is the associative law. And these are the some laws over here. A union phi absolutely is equals to A. A union A, that is the identity, that is equals to A. Fine. So that is the identity we have proved over here. You can go through this also. Very simple, this one. Now you have to solve one example. You can see here. Find S union Q and S intersection Q. Fine. Two sets are given to you. Okay, so what are the two sets? First one is S, which containing AB PQ, and Q is what? APT. So these are the two non-empty sets are given to you, and you have to find out union. So in the case of union, you have to find out, or you have to take here common elements first of all. So you can see here A, once A we have taken, B is present over here, we have taken B over here. P is repeated, we have taken P for once, and here is QT, here is QT. So that is the union. Fine. Now in the case of intersection, we have to take only common elements between. Okay, so common elements between S and Q. So what are the common elements between S and Q? Simply you can see here. Here is A, here is A, we have taken A over here. Here is P, we have taken P over here. So that is nothing but the intersection. This one is intersection, this one is union. Fine. So that is the difference between union and intersection. Now the next one is relative complement means what? For example, let us consider A and B. Let us consider A and B. These are the two sets. Then relative complement of B in A written as A minus B. Relative complement of B in A is written as A minus B. Or simply it is nothing but all the elements present in A will be written rather than elements present in B. Okay. So that is A minus B. So A minus B is nothing but relative complement of B in A. Relative complement of B in A. And which is written as X where or X such a way that X belongs to A and X should not be, X belongs to A and X should not be belongs to B. Fine. So here I have missed this notation. Keep in mind, I am going to draw here line. X is belongs to, okay, so this is important. X is belongs to A and X is not belongs to B. Fine. Then next one, you can mention this as X where X such a way that X belongs to A and negation of X belongs to B. That is correct one. This correction is necessary over here. Fine. So that is the relative complement. We will be discuss the examples in the later part of this lecture. We have taken lots of examples. So okay, so no worry about the how actually it works, relative complement. Then what is meant by absolute complement? So in the case of relative complement, we are taking two general sets. But in the case of absolute complement, we are taking one set as a normal set and another set as a universal set. For example, E is the universal set and A is the normal set. Then what is meant by absolute complement? So that absolute complement is nothing but universal set minus A. That is the notation for absolute complement, and it is nothing but the absolute complement of A in E. Absolute complement of A in E. So it is nothing but E minus A, which is nothing but equals to negation of A. You can see here negation of A is equals to E minus A, or which is simply represented as X where or X such a way that X is belongs to E and X is not belongs to A. So that is nothing but the absolute complement. Or you can mention here X such a way that X is not belongs to A. That is another method. Or third one, X such a way that negation of x belongs to A. So these are the some terminologies with respect to the absolute complement. Fine. So you can see here, negation of E is equals to phi, means negation of universal set is equals to empty set. A intersection negation A intersection negation A, again it is equals to phi. A union negation A, which is universal set. Fine. Now let us consider one example is given to you, and that example containing three sets A, B and C. A containing 2, 5, 6, B containing 3, 4, 2 and C containing 1, 3, 4. Then find out A minus B, B minus A, and show that A minus B is not equals to B minus A. Means what? Relative complement. The relative complement does not follows associative property. It does not follow the associative property. It does not follows commutative property. A minus B is not equals to B minus A. It does not follows commutative property. So what will be the A minus B? So as per the definition, we have to take all the elements present in A rather than elements of B. So you can see here AB. So 2 is present, you should be skip 2. Okay. So rather than this 2, you can take here 5, 6. So that's why we have taken here 5, 6. There is no need of this 3, 4 because 3, 4 these are the elements belongs to B, and 2 is present in both A and B. So that's why we are not going to take this 2 also. Fine. Now B minus A. So B minus A, definitely B minus A. All the elements present in A, all the elements present in B rather than elements in A. That is a 3, 4. So you can conclude here A minus B is not equals to B minus A. Again, you can find out these some examples. You can go through this screen and solve this example. And the last one is symmetric difference or Boolean sum. The last point, that is talking about the operations on set. So 7 operations are there. So 7th one is what? Symmetric difference or Boolean sum. So let us consider A and B, these are the two sets. Then what will be the symmetric difference, which is simply represented as A plus B or A triangle B. Actually, I does not mention over here, but A triangle B, it is also notation for symmetric difference or Boolean sum. So A plus B, which is equals to A minus B, means symmetric difference of B in A union symmetric difference of A in B. So that is nothing but the symmetric difference. That is nothing but the symmetric difference. I'm once again repeating here, A plus B. Just wait for a moment. This A plus B is nothing but the symmetric difference or Boolean sum, which is nothing but relative complement of B in A. Relative complement of B in A union relative complement of A in B. So that is nothing but the symmetric difference or Boolean sum. Fine. So you can go through this one also. What it containing? Which is exclusive disjunction. That is A plus B is equals to B plus A, means it follows the commutative property. A plus B plus C is equals to A plus in bracket B plus C, means it follows the associative property. A plus phi is equals to A plus A is equals to phi. Fine. Simple is there. We shall prove A plus phi is equals to A for X. So that is the terminology for proving this. You can go through this equation also. So basically what we have seen, in the case of set operation, we have seen total 7 set operations. First one is the intersection, then disjoint, mutually disjoint, then union, then relative complement, absolute complement, and Boolean sum, or it is also called as a symmetric difference. So keep in mind, if in the examination operations on set is there, you have to write down these 7 set operations and mention all these terms. Okay. Now the next point, we are going to solve some examples. Cartesian product. For example, A is the one set given to you, which containing 2 elements AB and B is equals to 1, 2, 3. You have to find out here A cross B. So what is meant by A cross B? It is called as a Cartesian product, or it is also called as a direct product, and which is nothing but A cross B, which is equals to, in curly braces, ordered a pair X comma Y such a way that X is belongs to A and Y is X is belongs to A and Y is belongs to B. Means whenever you are going to finding here ordered pair X comma Y, this X should be present. This X should be present in the first set and Y should be present from the second set. Now, from the given these two sets AB and 1, 2, 3, you can see here. You can see. Okay, so you can see here A1, that is A1, then A2, that is A. Just wait. A1, A2, and A3 is there. A1, A2, A3 is there. Then you have to take B1, B2, B3. So sorry for this. Here is actually 1. B1. You have to consider this as a B1, B2, and B3. So that is nothing but A cross B. And keep in mind that Cartesian product does not follows commutative property. Means what? A cross B is not equals to B cross A unless and until both the sets are similar. If both the sets are similar, then definitely A cross B is equals to B cross A. And there is none of business for naming this as a and B separately. Because if A and B are same, then why we take A cross B? We should take A cross A and which will be alternatively equal to each other. No issue about that. Now, B cross A is equals to B cross A means what? So whenever B cross A, you have to consider elements from B as a domain and elements from A as a range. So you can see here 1. Okay, so you have to take this as a 1 as a domain over here, range as a B, range as a A. Then 1B is there. Okay, then 2A, 2B is there, and 3A, 3B is there. So that is nothing but the B cross A. Then next one, B cross B. Both the domain and range should be from this 1, 2, 3. And as it containing 3 elements, B cross B, which gives you 9 ordered pair. You can see here 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. So total 9 ordered pairs are there. And finally, you can see here A cross B intersection B cross A. So A cross B is not equals to B cross A, as we find out here. A cross B having totally different ordered pair and B cross A having totally different ordered pair. So A cross B intersection B cross A, which is equals to what? As we know that A cross B is not same as B cross A, hence it does not follows commutative law, and A cross B intersection B cross A is equals to 5. So that is our example, very first example. Keep in mind, it is very important example. You have to solve this. Now we have to draw some Venn diagrams. Or before going to the Venn diagram, we have to find out this result. A plus in bracket B intersection C for this given 3 sets A, B, C. So you have given 3 sets A, B, C. A is equals to 1, 2, 3, 4, 5. B is equals to 1, 2, 3, 4, 8. C is equals to 1, 2, 3, 5, 7. And by using this, you have to find out A plus in bracket B intersection C. So as per the property of bottommost, we are going to find out here B intersection C or C intersection B. So if you find out here B intersection C, you have to take the common elements between B and C. So 1, 2, 3 is the common over here. Again 1, 2, 3 is common over here. So that's why B intersection is equals to 1, 2, 3. So you can see here 1, 2, 3 we have find out. So you can see B intersection C. B intersection, that is a 1, 2, 3. 5, 7 is dedicatedly for this C and 4, 8 is dedicatedly for this B. 4, 8, 1, 2, 3 which is the B set. 1, 2, 3, 5, 7 that is the C set, and 1, 2, 3 is nothing but the intersection of B and C. Now second one, we have to find out A plus B intersection C. So basically we got here B intersection C. So what is the B intersection C? B intersection C is nothing but 1, 2, 3. B intersection C is nothing but 1, 2, 3, and A is the set already given to you. A is the set already given to you. So what you have to perform? You have to perform here A Boolean sum or symmetric difference with respect to B intersection C. A Boolean sum or symmetric difference with respect to B intersection C. So basically it will be A minus in bracket B intersection C union B union C bracket complete minus A. Fine. So we have to find out here A minus in bracket B intersection C, which is nothing but X, such a way that X belongs to A and X is not belongs to B intersection C. That is nothing but the relative complement. And B union C minus A is nothing but X, such a way that X is belongs to B intersection B union C, B union C, sorry, B intersection C, and X is not belongs to A. So hence A minus in bracket B union B intersection C is equals to 4, 5. A minus in bracket B intersection C is equals to 4, 5, and B intersection C minus A is equals to 5. Fine. And finally, as we know that this is the relative complement, first relative complement, this is the second relative complement. That is relative complement of B intersection C in A, relative complement of A in B intersection C. So both the values have given over here. So these are the values 4, 5 and 5. So finally A plus B intersection C is nothing but 4, 5 union 5, which is nothing but the 4, 5. Okay. So basically what we have to do, we have to draw the Venn diagram for this one. So from this given three sets, you can see here. Okay. From this given three sets, you can go through this. Okay. So here is the A, here is the B, and here is the C. And we have to find out the intersecting portion, that is nothing but this one and this one. So that is the A plus in bracket B intersection C. Okay, so that's all for this example. Now we have to draw Venn diagrams for different examples with respect to the given sets A, B and C. Three sets are given to you. You have to draw the Venn diagram for this A minus in bracket B minus C, which is equals to A minus B union A intersection B intersection C. So let us take here LHS. So B minus C will gives you 4, 8. Fine. A minus B minus C will gives you 1, 2, 3, 5. Then on the RHS we have to find out here. Just wait. On the RHS you have to find out here A minus B. So A minus B is equals to 5. And A intersection B intersection C is nothing but 1, 2, 3. Okay. If you go through this, you will get the idea. And RHS will be A minus B union A intersection B intersection C, which is nothing but 1, 2, 3, 4. So if you see here LHS, which gives you result as a 1, 2, 3, 5, and RHS also, which gives you result as a 1, 2, 3, 5. Okay, so LHS is equals to RHS, and by using this we can mention this highlighted portion for the given Venn diagram. Fine. So 1, 2, 3, 5. That is nothing but A minus in bracket B minus C bracket complete, which is equals to A minus B union in bracket A intersection B intersection C. Keep in mind this is very important example. Okay. Again, one more example I would like to solve over here. In bracket A minus B minus C, which is equals to A minus in bracket B union C. So already we have here A, B, C. So A minus B will be what? This 5 minus C. C is what? 1, 2, 3, 5, 7. So A minus B minus C will be equals to 5. Then on the RHS you have to find out A minus in bracket B union C, which will give you, first of all, B union C is equals to this set, and A minus B union C is equals to this 5. So basically if you see LHS is equals to RHS is equals to 5, means it will gives you the diagram like this one. There is a no shaded portion. Keep in mind, there is a no shaded portion. You have to draw this as it is. This is nothing but the Venn diagram for A minus B bracket complete minus C is equals to A minus in bracket B union C is equals to 5. Fine. Then next one, A union B bracket complete intersection C. So what will be the result for A union B? So you can see here 1, 2, 3, 1, 2, 3. You have taken here 1, 2, 3. 4 is common, taken common here, and 5, 8. So 5, 8. That is a union B. Then A union B intersection C. So what is A union B intersection C? So already we have result of A union B. You have to intersect with this term. So 1, 2, 3, 5, 7. You have to check common term between this one. You have to find out the common term between this one and this one. Okay. So common terms are 1, 2, 3 is there. 1, 2, 3 is there. 5 is there. 5 is here. Okay. So 1, 2, 3, 5. So that will be the result. So you can see here we have represented this sets ABC together. Okay. And here is what? This is the shaded portion, which is nothing but A union B intersection C. A union B intersection C. Keep in mind, this is nothing but the C. Mistakenly I have written this as a B. This is nothing but the C. Now I have taken here another set. So what that set I have taken? A is equals to 1, 2, 3, 4, B is equals to 2, 3, 4, 5, and C is equals to 3, 4, 5, 1. So what is A union B? That is the result. C is equals to 1, 3, 4, 5, and A union B intersection C is equals to 1, 3, 4, 5. Okay. So simply you can see here, you can see the shaded portion which having the common element 1, 3, 4, 1, 3, 4 and 5. Yes. So that is nothing but result for this one. Okay. Then next one, you have to draw the Venn diagram for this. So what it containing? A intersection B is equals to A intersection C, but condition is what? B should not be equals to C. So you can take here A is equals to 1, 2, 3, 4, B is equals to 3, 4, 5, 6, and C is equals to 3, 4, 7, 8. If you observe here B and C having only two elements as a common elements, other elements are different elements. So this condition is also satisfied. Now what we have to check? We have to draw the Venn diagram for A intersection B is equals to A intersection C. So what will be the A intersection B? Common elements between A and B, that is 3, 4. Fine. 3, 4 is here. This 3, 4 and 3, 4. Then common elements between A and C. Again it gives you 3, 4. Common element between B, C. Again it gives you 3, 4. B is not equals to C. Yes, absolutely. B is not equals to C. And hence it is nothing but this shaded portion, which is nothing but A intersection B is equals to A intersection C, but B is not equals to C. You can see here B is a totally different and C is a totally different. Only two elements are common and we have taken that two elements as a common element. So that is the Venn diagram for A intersection B is equals to A intersection C, but B is not equals to C. Then the next one, you have to find out Venn diagram for A minus B. A minus B you have to find out. So it is nothing but X, where X is belongs to A and X is not belongs to B. X is belongs to A and X is not belongs to B. So if I take here A is equals to 3, 4, 5, 6 and B is equals to 1, 2, 3, 4, then A minus B will gives you 5, 6, because it will be containing all the elements present in A rather than repeated element with respect to B and all the elements of B. So that is the A minus B. So A minus B is nothing but shaded portion right now, whatever the green shaded portion right now I am shading over here. So that is nothing but, that is the portion which is nothing but A minus B. Okay. Very, very important examples are these. These examples are very, very important. You have to solve these examples by looking towards this. Okay. Now the next one, A intersection B is equals to 5. So A is 1, 2, 3, 4, totally different set. B is equals to 6, 7. So A intersection B is equals to 5. Here is A, here is B. So A intersection B is equals to 5. There is a no shaded portion for the A intersection B is equals to 5. Fine. Then next one, A intersection B union A intersection C. So let us take A is equals to 1, 2, 3, B is equals to 3, 4, 7 and C is equals to 3, 4, 2. Then what will be the A intersection B? A intersection B which having the common element as a A intersection B as a common element as a 3, 4. Keep in mind this 3 just wait, A intersection B having common element as a 3, sorry for mistake. So common element as a 3, so this 3 is the common element, so rather than this 4 you have to mention here as a 3. Okay, then A intersection C again, so A intersection C, if you see here again 3 is the common element, again you have to mention over here. And what you have to do, A intersection B union A intersection C, which gives you common element as a 3, which gives you common element as a 3. You can see here, this is the shaded portion, which is nothing but shaded portion for what? A intersection B union A intersection C. Fine. So that's all for the Venn diagram. Let us see some examples which is related to the power set. So basically we have seen what is meant by power set. So for example, if one set is given to you, then all the possible subset is nothing but power set of the original set. It is the collection of all the subset which is with respect to the given set. For example, we have taken here these 3 examples. A is equals to ABC, B is equals to phi, and C is equals to X, Y, Z, and opening and closing curly. Fine. So basically, we have taken here first example. Capital A is equals to ABC. Capital A is equals to ABC. So what is the cardinality of A? Cardinality means what? Number of elements present in A, that is equals to 3. So the power set of A, that is P of A, or 2 raised to A, which gives you 2 raised to 3, which is equals to 8. Means number of subsets will be equals to this 8. Number of subsets will be equals to 8. So these are nothing but P of A, that is a power set. This is an empty set with the single element, that is A, B, C. Then set with the 2 elements, AB, AC, BC, and set with the 3 elements, ABC. So total number of elements 1, 2, 3, 4, 5, 6, 7, 8. So that is nothing but the power set with respect to the set A is equals to small a, B, C. Then B is equals to opening curly phi closing curly. So actually it is not a empty set, because in between two opening and closing curlies there is one element, that is a phi. So cardinality of B is nothing but 1, because one element is present, cardinality of B. So P of B is equals to 2 raised to B, which is nothing but 2 raised to 1, which is equals to 2. Means number of possible subsets is equals to 2. So hence you can write here P of B is equals to phi, and in curly braces phi. This phi and this phi having different meaning, or it is also represented as opening curly, closing curly, and here is what? Opening curly, phi, closing curly. So that is nothing but the power set of B, where B is equals to opening curly, phi, closing curly. Now the next one. The next one is, you can see here, C is equals to X, Y, Z, opening and closing curly. So cardinality of C is equals to 4, because it containing X, Y, Z as a 3 sets, X, Y, Z as a 3 elements, and opening and closing curly as a 4th element. So cardinality of C is equals to 4. So number of subset with respect to the C is nothing but 2 raised to cardinality of C, which is nothing but 2 raised to 4, which is equals to 16. So number of subsets in the given set, from the given set, will be equals to 16. So you can see here, this is the phi, X, Y, Z, and this is the one more set. Then X, Y, X, Z, X, and this empty set, or you can say phi. Then Y, Z, then Y null, Y phi, and Z phi. Then X, Y, Z, X, Y phi, X, Z phi. Then Y, Z phi, X, Y, Z phi. Bracket complete. Opening curly is matching with the closing curly. So total 16 subsets are possible whenever cardinality is 4. That is a 2 raised to 4. Now, one more example I would like to explain over here. Find out ABC of the given 3 sets. A is equals to 1, B is equals to AB, and C is equals to 2, 3. So basically, whenever you are given A cross B cross C without any parenthesis or bracket, You have to solve this from left to right because it deals with the ordered pair and ordered triple. So if you see here A cross B, which is equals to in curly braces x comma y, where x is belongs to A and y is belongs to B. Means we have to take the domain from the given ordered pair. You have to take this domain x from A and a range from B. So you can see here A cross B cross C, which is nothing but in bracket A cross B cross C, which is nothing but ordered pair x comma y, ordered pair bracket angular bracket complete, comma z, main angular bracket complete. So x belongs to A and y belongs to B and z belongs to C. So that is nothing but A cross B cross C. And finally it gives you A cross B which is equals to 1A. This is 1A, you can see here 1A and 1B. Here is what? 1B. 1A and 1B is here. A cross B. Then A cross B cross C. So you have A cross B with you and C with you. So what you have to do? So you have to take here the first ordered pair 1A. You can see here 1A. That is the element from the order triple. And take this to over here. Then 1B. 1A. Again here should be A. Keep in mind. 1A2, 1A3. Fine. 1A2, 1A3. Then 1B2, 1B3. That is 1B2 and 1B3. So that is nothing but the Cartesian product. So some terminologies we are going to discuss here. What is meant by power set? So the power set, if A is the given set, then power set of A is nothing but collection of all the subset including all subset. So power set of A is equals to 2 raised to cardinality of A. If A is equals to ABC, then cardinality of A is equals to 3. That is number of elements in A. And power set of A, which is nothing but 2 raised to 3, it will gives you 8 subsets. So you can see here 1, 2, 3, 4, 5, 6, 7, 8. So that is nothing but the power set. Then what is meant by proper subset or proper inclusion? So what is meant by proper subset? For example, a set X is said to be proper subset of Y if and only if every element of X present in Y and Y having additional element in it. That is X is not equals to Y. So you can see here X is equals to 1, 2, 3, Y is equals to 1, 2, 3, 4. X is not equals to Y. That is the condition for the proper subset or proper inclusion. And you can see all the elements of X are present in Y and 4 is the additional element with respect to this set X. So that's why this Y is called as a superset and X is called as a proper subset, or X is properly included in Y. X is properly included in Y. You can see here X is properly included in Y. Okay. Then next one, subset. A set X is said to be subset of Y if and only if all the elements of X are present in B. All the elements of set X are present in Y. Then X and Y are called as a subset of each other. You can see here A is equals to AB, B is equals to 1 ABC, C is equals to AB. So you can mention here A is a subset of A is a subset of B, A is a subset of C, A is a subset of C, B is a subset of B. Then B is not subset of A. You can see here because B having one more additional element as a C, and B is not subset of C. C is a subset of C, but C is not proper subset of C. It's not allowed. Keep in mind. Okay. Then next one, null set. Null set means what? A set does not contain a single element is called as a null set or empty set. It is denoted by far or it is denoted by opening and closing curly. Symbol for empty set is capital E. E is equals to phi, E is equals to opening and closing curly, phi is equals to opening and closing curly. Cardinality of E is equals to 0. That is the null set. Then universal set. What is meant by universal set? The set is said to be universal set if and only if it contains all the sets as a subset under the discussion. Means for example, if 3 sets are given to you, or more than 3 sets, not necessarily only 3 sets, 1, 2, 3, 4 up to infinity. If all the elements of the given sets are included in a particular set, then that set is called as a universal set. You can see here A is equals to 1, 2, 3. This 1, 2 is included over here. B is equals to 2, 3, 6, 7. That 2, 3 is here. 2, 3 is here and 6, 7 is here. Okay, means B is also included. And talking about C, 4, 9 is also included. So that's why you can say here all the elements of A, B and C are belongs to set capital U, that is nothing but the universal set. It is represented by capital U or it is represented by capital E. Okay, so universal set is the superset under the discussion which covers all the subsets in that particular set. And the next one is Cartesian product. Let us consider A and B. These are the two sets. Then Cartesian product of A and B is written as A cross B. A cross B is equals to ordered pair X comma Y, where X is belongs to A and Y is belongs to B. For example, if A is equals to AB and B is equals to 1, 2, then A cross B, definitely it will be gives us 4 ordered pair because it containing 2 elements. Second one is also containing 2 elements. So 2 cross 2 is equals to 4 ordered pairs will be gives to you. So domain will be made up of A and range will be made up of this B. So the first ordered pair will be A1, second one will be A2, then B1 and B2. So that is the Cartesian product, or it is called as a direct product. You can see here cardinality of A cross B is equals to cardinality of A cross cardinality of B, that is A cross B. Number of ordered pairs in A cross B is equals to cardinality of A cross B. Already we have seen over here, that is 2 cross 2 is equals to 4. Then ordered pair, you can see the ordered pair is a proper sequence of element or objects which having fixed meaning. So it is generally denoted as angular bracket X comma Y, where X is called, the first element is called as a domain, or the first object is called as a domain and second object is called as a range or codomain. Here X is a domain and Y is a codomain. If X comma Y is equals to U comma V, then there should be X is equals to U and Y is equals to V. Then ordered pair X comma Y and U comma V are said to be equals to each other. Then the next one, symmetric difference or Boolean sum. So what is meant by symmetric difference? It is denoted as A plus B. Means for example, if A and B are the two sets, then it is represented by A plus B, or it is denoted by A triangle B. That is nothing but the symmetric difference or Boolean sum. And which is same as A plus B is equals to A triangle B, which is equals to A minus B union B minus A. That is relative complement of B in A and relative complement of A in B. So if A is equals to 1, 2, 3, B is equals to 2, 3, 4, then A minus B is equals to 1, B minus A is equals to this 4, and finally A plus B is equals to A triangle B is equals to 1, 4. So that's all for the symmetric difference or Boolean sum. So what we have discussed in this chapter, what are the important points from the chapter number 2? So first one is the set. You have to define what is member set. Set is nothing but collection of similar or different sort of elements or member functions, or it is also called as objects. So generally the set is classified into two types. First one is the finite set, infinite set. Again on the basis of some different properties which containing proper subset, or it is called as a proper inclusion, then power set, null set, universal set, and likewise. So that is nothing but the set. Then different operations on set. So basically set having 7 operations. First one is the intersection, then disjoint, then mutually disjoint. The next one is the union, then symmetric difference, or it is called as a Boolean sum, relative complement, and last one is the absolute complement. Then we have seen some example which is related to the Cartesian product. Keep in mind, that is very important. Then we have seen what is meant by Venn diagram. Venn diagram we have to prepare. Then what is meant by power set. So power set is nothing but, for example, let us consider A is the given set with some elements. Then power set of A is nothing but P of A, which is equals to 2 raised to n, where n is number of elements present in the set A, and which consists of all the possible subset which is made up of elements which is present in A. Then we have seen some terminologies which is related to what is meant by power set, what is meant by proper subset, then Cartesian product, ordered pair, what is meant by subset, null set, universal set, proper inclusion, and symmetric difference. And finally, we have seen one example which is of Cartesian product. So guys, that's all. Or these are the important points which is for the unit number 2. I am suggesting this as an important point. Don't believe totally on these points. Just I am claiming this may be asked for the university examination. Okay, so thank you so much for your patience listening. Thank you.